Hello, my name is Philip Banks, and on behalf of my colleagues at Torbjörn Holmberg and Magnus Carlsen, I'm going to share with you the results of a very interesting case study on intermediate bus architecture system efficiency optimization that Ericsson presented at Darnell Power Forum 2010. This case study will present the results of Ericsson's findings of using a novel optimization algorithm to optimize intermediate bus voltage, which results in significant energy and cost savings, while increasing reliability. In this presentation, we will recapitulate on a technology introduced to the datacom industry in the late 90s called Intermediate Bus Architecture, IBA, and to present the latest evolution of the Intermediate Bus Converter, IBC, which has now moved from being a passive power source, converting a system voltage to subsystem only, to an active, intelligent power source, the Advanced Bus Converter, ABC. The simulation environment is based on models extracted from a combination of a series of Ericsson 3E point-of-load voltage regulators, BMR450, and BMR451, powered by an Advanced Bus Converter type, BMR453. I will end this presentation by giving the results of this case study and outcomes from the simulation, such as efficiency improvements and how suitable the algorithm is for future implementation in the embedded firmware of a digital power controller or within a board power manager. Firstly, what is a conventional intermediate bus architecture and what is an intermediate bus converter? In the late 90s, facing an increase in demand for sub-5 volts high current microprocessors and associated components, combined with high system integration costs, the datacom industry introduced a new power architecture concept based on a main onboard DC-DC converter, converting 48 or 24-volt system voltage into a single board voltage, which powered a range of voltage regulators known as point-of-load. Intermediate bus voltage varies from application to application and is defined by designers to reduce distribution power losses in copper traces and interfaces, but also to reduce power losses at point-of-load level when stepping down intermediate bus voltage to payload requirements. For example, for small systems, designers tend to use a 5-volt bus voltage, prioritizing step-down optimization. In large systems, designers will choose a 12 volts bus voltage to reduce power losses in distribution. This architecture was named Intermediate Bus Architecture, IBA, and the main onboard DC-DC converter named Intermediate Bus Converter, IBC. In this architecture, the IBC and point-of-load performances are limited to the intrinsic performances of each module, set by design optimization during their development, resulting in unoptimized topology and unnecessary power losses when the payload is below the optimal conditions. Recent data center studies show this is true in more than 80% of cases. Information and communication technology covers a very large range of applications such as radio base stations, data storage, routers, and data centers. These have different power demands, and designers rapidly concluded that a fixed intermediate bus voltage was not the most optimized solution to power systems which have large variations in their utilization, from almost no traffic data to the limit of saturation. To respond to this, in 2008, Ericsson launched the first digitally controlled advanced bus converter, the BMR453. This is based on a digital core controller and an embedded communication interface, complying with the Power Management Bus Standard, PM Bus, and was the first advanced bus converter offering the possibility to adjust the intermediate bus voltage to payload condition in real time. In addition to the BMR453, and based on the same concept of using a digital core controller and a PM bus interface, Ericsson added a series of point-of-load voltage regulators, the 20-amp BMR450 and the 40-amp BMR451. These are both able to adjust their performances to the payload condition. One immediate benefit offered by such products is to precisely trim bus voltage to optimize performances to system demand. Modeling power losses in a switching mode power supply is in theory not too complicated and is represented by this equation. In practice, however, it is much more complicated than it seems to be, which is why we decided to base our algorithm on a matrix of data measured from a set of devices. This allows us to verify the correlation of the measurement to the simulation. To support this case study, we have used one advanced bus converter, BMR453, to power two Ericsson 3E 20-amp BMR450 and four 40-amp BMR451 point-of-load voltage regulators. We then measured all parameters at different points of operation, from no load to full load. And from these measurements, we created polynomial models by compiling the data collected and using the least square fit model. Then the polynomial models have been used in the Simulink simulation system. To give you an example of the array of data we have measured and collected from each individual power module, here are the results for one of the 20-amp BMR450 used in this case study. The output voltage of this specific one has been trimmed down to 1 volt, the load adjusted from 0 load to 20-amp full load, and the input bus voltage adjusted in the range from 4.5 to 14 volts. We then measured power losses across every point of operation. The same procedure has been conducted for all products, including the advanced bus converter BMR453. The data was entered into the master database to create a parametric model, which was then used in the simulation system. Once we had entered all the measurements into the database, we used them to create polynomial models. We then compiled and uploaded all the models into the Simulink model that we have summarized in this diagram. The model includes one advanced bus converter, BMR453, converting system voltage that varies from 36 to 75 volts, to an intermediate bus voltage which powers the 6 points of load, two 20-amp BMR450 and four 40-amp BMR451. To dynamically control the intermediate bus voltage and to optimize system performance, we added an algorithm which collected the data to create the simulation model and delivered instructions to the BMR453 to adjust the intermediate bus voltage to an optimum value for a certain load condition. Now we've seen the system, let's have a look at the optimization algorithm.